This film presents high-speed movies of pool boiling and free convection from a wire immersed in carbon dioxide. The carbon dioxide is near its critical state of 73.8 bars and 31.1 degrees Celsius. Below the critical point, there may be free convection, nucleate boiling, or film boiling. Above the critical point, only free convection is possible. The apparatus includes a high-pressure cylinder in which a platinum wire is mounted. The wire is connected to an external power supply which is used to control the heat flux from the wire. The ends of the cylinder, which contain the two viewing windows, are bolted in place. Extension tubes are added in front of the viewing windows. These tubes fit between the cylinder and the walls of the constant temperature bath into which the cylinder is placed. They prevent the distortion which would result from photographing through the liquid in the bath. When filming, the apparatus is arranged as shown in the figure. Light from a high-pressure mercury arc passes through the chamber, and images are recorded with a high-speed camera. Film speeds of 1200 to 2000 frames per second are used. Thus, each scene will last from 50 to 85 times as long as the actual process. Both the cylinder pressure and the heat flux from the wire can be controlled. At pressures less than the critical pressure, the carbon dioxide is maintained at the corresponding saturation temperature. The heat flux from the wire is calculated from the measured voltage drop in current. The voltage drop and corresponding current are also used to calculate the electrical resistance of the platinum wire. The wire temperature is determined from the calibration of resistance as a function of temperature. The experimental results are used to construct a plot of heat flux versus temperature difference. The vertical scale represents the heat flux from the wire measured in watts per meter square. On the horizontal axis, the temperature difference between the wire and the saturation temperature of the carbon dioxide is plotted in degrees Celsius. A logarithmic scale is used for both axes. The results of an experiment at a pressure of 65 bars are shown. This is well below the critical pressure of 73.8 bars. When low power is applied to the wire, natural or free convection takes place. When the wire temperature is slightly above the saturation temperature of the liquid, bubbles begin to form in the wire. As the heat flux is further increased, the temperature difference between the wire and the saturation temperature also increases. This part of the boiling curve, where vapor bubbles form on the wire, is known as the nucleate boiling regime. The nucleate boiling regime is terminated at the burnout point. Here, a slight increase in heat flux causes a drastic increase in the wire temperature. Nucleate boiling from the wire is replaced by film boiling. In the present system, the current in the wire is controlled by a constant voltage source. Thus, the sudden increase in wire temperature and corresponding increase in wire resistance results in a slight drop in heat flux. Providing the wire temperature does not exceed its melting point, film boiling will continue as the heat flux from the wire is increased further. On decreasing the heat flux, the film boiling process does not retrace the original curve. Instead, film boiling persists below the burnout heat flux until eventually a sudden decrease in the wire temperature accompanies the return to nucleate boiling. The dashed portion of the curve is an unstable transition regime between nucleate and film boiling. This region could be investigated with an apparatus in which the temperature difference rather than the heat flux is controlled. As the pressure is increased, the burnout heat flux decreases, as does the corresponding temperature difference. This film shows boiling not only at 65 bars, but also at 68, 72, and 73.6 bars. At this last value, the system is nearly at the critical pressure of 73.8 bars. Also shown is single-phase natural convection at a pressure of 75.5 bars, well above the critical pressure of carbon dioxide. In the boiling photographs which follow, the pressure is maintained constant during each scene, while the heat flux is varied. In this first scene, the carbon dioxide is at a pressure of 65 bars with the corresponding saturation temperature of 25.5 degrees Celsius. During the run, the heat flux is gradually increased to a maximum of 450,000 watts per meter square. This is below the burnout heat flux, and nucleate boiling exists throughout the entire run. Note the large variation in the bubble departure diameter along the length of the wire. As the heat flux increases, so do the diameters of the bubbles. The bubble motion on the underside of the wire also increases as the heat flux is increased. As the bubbles grow and leave the surface of the wire, coalescing of small bubbles into larger bubbles can be observed. In this scene, the pressure is again 65 bars, but this time the heat flux is abruptly raised to a value of 300,000 watts per meter square. It is then gradually increased to 500,000 watts per meter square as the scene progresses. Film boiling is immediately established on the wire, even though the heat flux is less than the burnout heat flux. Note that film boiling can be established without passing through the nucleate boiling regime and the burnout point. The wire is enveloped in a vapor film from which the boiling takes place. The pressure is now increased to 68 bars, and the carbon dioxide is at the corresponding saturation temperature of 27.5 degrees C. The initial heat flux of 200,000 watts per meter square is near the burnout point. During the run, the heat flux will be steadily increased through the burnout point to a value of 300,000 watts per meter square. As the heat flux passes through the burnout point, we see an abrupt change from nucleate boiling to film boiling all along the wire. The film boiling in both this and the preceding scene is similar to that encountered far below the critical pressure. The pressure is now increased to 72 bars with the corresponding saturation temperature of 30 degrees Celsius. The initial heat flux of 20,000 watts per meter square is gradually increased to a value of 200,000 watts per meter square as the run progresses. Initially there is nucleate boiling. With increasing heat flux, the transition to film boiling takes place. Notice that at this pressure, vapor columns leave the envelope around the wire, whereas with film boiling at lower pressures, the vapor left in large bubbles. As the heat flux is further increased, the vapor columns give way to vapor sheets. The tops of the vapor sheets oscillate, producing turbulent bursts. The bursts commence closer to the wire as the heating rate increases. Bubbles continue to form at the top of the vapor sheets. The next run is again at a pressure of 72 bars. The power is abruptly raised to 350,000 watts per meter square and then gradually increased to 500,000 watts per meter square. We again see the oscillation of the vapor sheets and the turbulent bursts. As the heat flux is increased to its maximum value, the turbulent bursts are very close to the wire. Bubbles rise from the tops of the turbulent bursts. In this scene, the pressure is 73.6 bars, very close to the critical pressure of 73.8 bars. The bulk temperature is the corresponding saturation temperature, 30.9 degrees Celsius. The heat flux, initially 2,000 watts per meter square, is increased during the run to 300,000 watts per meter square.